The Web3 ecosystem is expanding rapidly, snapping new financial infrastructure into place almost daily. Developers now have access to a robust set of base layer primitives. We have yield vaults generating passive returns, automated market makers, or AMMs, which are decentralized exchanges that rely on mathematical formulas to price assets, and Layer 2 networks, secondary frameworks built on a main blockchain to scale transaction throughput. This is the reality. Hundreds of distinct, powerful protocol nodes are entirely disconnected. Primitives floating in isolation are useless if they cannot communicate. To wire them together, developers must construct custom, hard-coded back-end logic for every single connection. Writing this manual wiring is incredibly expensive. Every new integration requires weeks of custom Solidity code. Solidity is the primary programming language used for creating smart contracts on Ethereum. That custom code introduces severe security risks. Because the logic is bespoke, protocol teams must pay for expensive, redundant security audits every single time they alter how their application interacts with another protocol. Even after those audits, these hard-coded backends remain inherently brittle. If an underlying protocol updates its smart contracts or changes its fee structure, the custom integration breaks, taking the dependent application offline. The primary friction limiting decentralized applications is no longer a lack of financial building blocks. The bottleneck is the execution layer required to connect them. When developers add a new protocol to a multi-chain application, architectural complexity doesn't scale linearly. It scales exponentially, as every new node must be explicitly reconciled with the existing logic. This creates massive technical debt. Engineering teams end up spending the majority of their time simply maintaining old integrations to keep the app functional, instead of innovating on the core product. Protocol teams burn significant portions of their budget manually wiring these primitives together. Capital that should be deployed toward user acquisition or feature development is swallowed by basic infrastructure plumbing. There is a lingering misconception in the industry that building proprietary smart contract integrations from scratch is the only way to ensure ultimate security and control over a protocol. In reality, a unified, battle-tested execution layer provides a stronger structural solution to these integration vulnerabilities, standardizing the exact pathways where exploits typically occur. To successfully scale cross-chain applications, builders must abandon bespoke integration scripts in favor of programmable middleware. This diagram shows two ways to execute a specific operational scenario: taking a base asset, routing it through a decentralized exchange, bridging it to a Layer 2 network, and depositing it into an ERC-4626 vault. ERC-4626 is a tokenized vault standard that optimizes and standardizes the technical parameters of yield-bearing tokens. Looking at the manual path on the left, the developer must write distinct smart contract interactions to first swap the asset and then bridge it across networks. Each of these steps generates intermediate tokens and extracts separate gas fees. Next, the developer must sequence the final contract calls required to bridge the asset into the yield vault. This chain creates multiple points of failure where slight slippage or gas calculation errors can cause the entire transaction to revert. Enso was designed to replace this entire sequence. It serves as a standardized execution engine explicitly built for these complex workflows. On the Enso path on the right, the exact same cross-chain transaction is executed completely differently. A single clean vector passes directly from the initial asset to the final vault deposit. The execution engine handles complex liquidity sourcing, token routing, and multi-chain messaging invisibly on the backend, without requiring the developer to script intermediate hops. The final state of the user's assets is mathematically identical in both scenarios. The difference is that the engineering overhead required to build and maintain the application drops to near zero. Utilizing a centralized execution engine eliminates the brittle, multi-step smart contract interactions that currently plague cross-chain development. The architecture that makes this possible is Enso's core functional unit, the shortcut. This diagram illustrates what a shortcut actually is: a modular, reusable computational path. Enso acts as a central hub, using standardized output nodes to route logic perfectly to over 200 different protocols. A shortcut abstracts complex, multi-step actions like lending, swapping, and rebalancing, and collapses them into a single executable API call. An API, or Application Programming Interface, is a set of rules that allows different software applications to communicate with each other. For developers, this instantly cleans up their back-end architecture. It removes the need for thousands of lines of custom integration code. Instead of studying the individual smart contract mechanics of a target protocol, developers simply plug into the Enso shortcut. That single connection grants immediate access to deep liquidity across the entire ecosystem. When an underlying protocol upgrades its contracts or alters its parameters, Enso updates the corresponding shortcut globally. The developer's application continues functioning without requiring any manual maintenance or fresh audits. The shortcut framework allows teams to shift their engineering resources away from basic infrastructure maintenance and reallocate them directly toward product innovation. This abstraction prompts a structural question. How can advanced autonomous front-end applications reliably execute multi-step on-chain actions if they are no longer housing massive execution libraries themselves? The first clear use case for this standardized execution is automated asset management. Vault operators use Enso's clean logic pathways to seamlessly deploy complex yield generation frameworks across multiple chains simultaneously, without rewriting their core strategy contracts for each network. The second primary application is Bitcoin Decentralized Finance, or BTC-Fi. Historically, there has been a severe composability gap between Bitcoin native assets and the logic-heavy environment of the Ethereum Virtual Machine, or EVM. Enso bridges this gap at the infrastructure level. Its shortcuts allow Bitcoin assets to interact cleanly with EVM lending markets and automated market makers, circumventing the usual friction of cross-chain asset wrapping. The ultimate test of this execution infrastructure is DeFi, the intersection of artificial intelligence and decentralized finance. An autonomous AI agent requires a real-time execution layer to move liquidity and manage assets. Data alone is insufficient. The agent needs a direct pipeline to finalize on-chain transactions. As shown in this schematic, a single decision signal from the agent logic core triggers Enso to autonomously deploy liquidity across 3 protocols. Consumer-facing Telegram bots rely on this exact same back-end logic to execute rapid, social trading flows entirely through chat interfaces, abstracting the blockchain away from the end user. Enso acts as the essential execution API that makes these autonomous applications computationally viable. The mechanics of this abstraction layer are sound in theory, but its utility is proven by its empirical track record in the live market. As the central router, Enso actively powers the back-end logic for over 75 decentralized applications. Through these, it has enabled over $15 billion in volume, operating with zero funds lost to smart contract vulnerabilities. This shift mirrors the historical scaling of traditional Web2 infrastructure. Enso provides the same structural utility for decentralized execution that Amazon Web Services provided for server hosting, or that Stripe provided for digital payments. Every major wave of technological expansion relies on an invisible infrastructural layer that handles the heavy lifting, allowing the application layer to scale rapidly. For Web3 builders, this represents a definitive shift in engineering strategy, entirely eliminating the technical debt of maintaining fragmented protocol integrations. By adopting a unified execution engine, protocol teams can stop wasting cycles building basic plumbing and dedicate all their capital to shipping highly optimized products.